Now, so far we've looked at what's known as combinational logic, which means we have basically a cascade of logic gates and the output is a simple function of the input. So it's a Boolean function. But this is not actually the type of logic that's most common or preferred in FPGA digital design. There's another type of logic called synchronous logic, which incorporates the clock into the digital design. And we're going to look at an example in this video of using a clock input from the push button. Okay, if you notice, there are actually two push buttons on the DE0 Nano board. When you push those buttons, you get a very clean negative edge, and you can use that negative edge as a clock. And in synchronous logic, the update of the logic will only happen on the negative or positive edge of a clock. And this is actually extremely important in complex designs, because if you rely simply on a very large cascade of logic gates to do your design, you are asking for trouble, because obviously when you put data into that cascade of logic gates, there's going to be propagation delays separating the input and the output, and there's going to be propagation delays between each of the gates as well. And what you can get is instability, what's known as metastability, where those signals which are racing around the FPGA at the speed of light, they arrive at their destination gate at different times, and that can easily lead to instability. When you incorporate a clock signal, the update of the logic will only happen on the positive or negative edge of a periodic clock signal, and that gives time for all of those signals to reach their destination gate before the update happens. So as long as you can guarantee that all those signals reach their gates within the specific amount of time during the clock period, you've got a much better chance of having a stable design. So let's convert our multiplexer into a synchronous multiplexer. Let's start with this one. So what we want to happen is for the clock to come into this module, and we want that to be in the sensitivity list. So the code within that block will only execute on the positive or negative edge of the incoming clock. So in the case of our multiplexer, it should only update, so the output should only change on the positive or negative edge of the clock. It doesn't matter anymore whether the select input or A or B change. It has to wait until the negative edge of the clock before the output will change. And that's a kind of synchronous logic. So what I'm going to do is I'm going to copy this code, and I'm going to start a new Verilog HDL file, and I'm going to rename that to multiplexer behavioral clock, and I'm going to introduce a new input called clock. And that clock is going to be taken from one of the push buttons on the Nano board. And remember, that push button will give you a nice clean negative edge. Now the always block now, rather than having A, B or select in the sensitivity list, we're going to change that to negative edge of clock. And what that means is whatever's inside this block, that will only execute on the negative edge of the clock. Now, technically, I should change these to non-blocking assignments, but don't worry too much at this stage about the significance of the non-blocking assignment here. Right, so let's save this as a new module. Make sure it doesn't go in output files. You can see I've already got one from earlier here because I tested the design. So that's called multiplexer behavioral clock. I'm going to create a symbol file. Oh, there's a mistake. So we haven't declared the clock as the input. Okay, that's an easy fix. Create the symbol file, and then we can delete the old one and put the new one into our design. You can see we have an extra input for the clock, and what we can do now is have an input pin, and we can put that input pin into the clock. This is going to be coming from the push button, so I'm going to rename that push button. So let's save. Now, because we've changed the pins, we need to do analysis and elaboration. Now, we need to consult the user manual for the DE0 Nano board, and you can see that key 0, which is this one, that has an assignment J15. So now if we go to the pin planner, you can see I've already done it for a different pin here, so I retained that from last time. But push button, we're going to call that J15, push button. Right, okay, so that's now associated with the push button, so we can save and we can do compilation. Now, what we expect to happen now is if we change any of the inputs here, we don't expect any update to happen on the output before the user pushes the button. Okay, so we're going to test that now. So let's go to Tools, Programmer, and then Start. So let's have a look at what we have. Now, first of all, let's change the inputs. This is the select pin. Nothing's happening. Let's change the two inputs. Nothing is changing. Let's push the push button. So the push button, nothing changes. But if I change the select pin, we expect the output to change because the inputs are different. So if I push the push button, you can see the output goes to 1. But that only happened when we pushed the push button. If I change the select pin again, nothing happens until I push the push button. So the update only happens on the push of the button because our sensitivity list is looking for the negative edge of the clock before this code will update. This is an extremely important thing to understand in Verilog because most of our logic will actually be synchronous to the positive edge of the clock. This one is negative edge. It's a special case because the push button here happens to give a negative edge rather than a positive edge. But on this board, we actually have a clock, a 50 megahertz clock, which goes into the FPGA, and that's when we can start doing things very, very fast because 50 megahertz, 50 million cycles per second, we can run our logic very, very fast and in a synchronous way. So this was an introduction to synchronous logic in the context of our multiplexer. I'll see you in the next video.